K. Senthilkumaran, currently working as Associate Professor in Indian Institute of Information Technology, Design and Manufacturing, IITDM, Kanchipuram, Chennai, India. He obtained his doctorate in Additive Manufacturing in the Mechanical Engineering Department of Indian Institute of Technology, Delhi. He previously worked as guest researcher in the Systems Integrated Division of National Institute of Standards and Technology, United States of America. His research interests are in additive and sustainable manufacturing. He is currently the associate editor of ASTM, a reputed journal on smart and sustainable manufacturing. He is also member of many international bodies, ASME, SME, SAE, and IEEE. He is also a member of IFIP WG 5.7, which is involved in developing smart manufacturing technologies. He has been nominated as for a prestigious in-residence program for inspired teachers at Rashtrapati Bhavan, New Delhi in the year 2016. He has published 54 international publications in international peer-reviewed journals and conferences. He is also a regular speaker at various design and manufacturing workshops and events on design and manufacturing. He has taught more than 10 courses on design and manufacturing and maintains an online portal called manufacturingportal.in for blended learning in design and manufacturing education. He was the coordinator for a teaching learning center from 2020 to 2023 at IITDM, Kanchipuram, funded by Ministry of HRD, Government of India, which develops affordable digital fabrication technologies for colleges, polytechnics, and schools for STEM. He is also the in charge of Smart Manufacturing Lab at IITM, Kanchipuram, funded by Ministry of HRD, Government of India. Now I would like to welcome Sir Professor K. Senthilkumaran Garu for taking over the session, sir. Welcome, sir.
Thank you for the warm introduction. Am I audible?
Yes, sir. Yes.
Am I audible?
Yes, sir. Yes, sir. You're audible.
Oh, great. Okay. So I think I would like to thank Dr. Janardhan for this short and sweet introduction of mine. So I think I believe I am the last speaker for this workshop. So I believe that all of the participants would have received excellent information and knowledge from many of the speakers. So before I begin my session, so I would like to set up my PowerPoint presentation. So please pardon with me for a few minutes to just get the slides ready. Are you able to see my screen?
Yes, sir. We can able to see your
slide. It's visible, sir. It is visible.
Oh, screen is visible. Okay.
Yes, sir. Visible, sir.
So is my slides moving?
Yes, sir. It is moving, sir. Moving.
Okay. Thank you. So thanks for the confirmation. So I think I would like to make my session as you know as large focus as a systems level, right? So I think we have seen production process when we talk about conventional manufacturing or additive manufacturing. So we always see them as a process to convert raw material to finished goods, right? So in my lecture, so I'm looking at some systemic challenges and systemic opportunities. When we look at the big picture, not just the small m, where the material conversion happens, layer by layer, point by point, strand by strand, right? So we look at more from the perspective of how it changes the dynamics of the entire production and supply network, right? So this perspective is very hard to get, from many of the workshops that you have earlier attended. So I am planning to basically take my session in a direction which helps participants to understand the past, the present, and the future, and how it affects our existing production networks and supply chain, and what are the different types of enablers, and then what are the different challenges and risks associated with the production network. So even though my research spans in design for additive manufacturing, especially around developing digital twins and things like that, so I also have research interest in understanding the economics of additive manufacturing. Recently, one of my product on decision support system for moving from conventional to additive. So by using product lifecycle management tools has been commercialized, right? So that's the kind of work that we do. So we work at different scales within the production, right? So let us just try to understand today's agenda. So today's agenda is going to be first I will be beginning to discuss the cultural shift that is happening in the manufacturing industry, especially around everybody wants a pie, right? So China being the dominant manufacturing, uh, as a factory house or a production house of the entire world. So everybody wants to basically reshore it. So looking from that supply chain, geopolitical perspectives, and also how production chains and networks are being drastically changed by additive manufacturing. So we'll try to look at it more from the modern evolution of manufacturing and also the changing customer preferences and how additive manufacturing influences that decision making in everyday life, right? So that's the kind of theme I have set the tone. I hope I have seen your, the layout of the different kinds of speakers that you had. I know you already have received a good amount of knowledge about additive manufacturing, design from design perspective, from material perspective, from process perspective, and also from science perspective, where you would have understood about how to understand the science behind the first principles of laser melting, laser consolidation, laser cladding, and then electron beam melting, electron beam based surface modification or cladding or deposition type of process. So hopefully, I think I would summarize the entire program in a broader impactful approach, where how the production process could improve the overall supply chain efficiency, security, information sharing, coordination, and all those aspects, even responsiveness, right? So we'll see that a little bit more from that perspective. So which helps you to basically do research without much capital intensive equipment materials. So many times, when we want to work in additive manufacturing, but we are constrained by the resource, constrained environment. So like the previous Professor Karnagaran was just mentioning that he comes from a very resource rich environment. So many of the researchers in this country are also from the resource poor environment. So a resource constrained environment. So where using these kinds of approaches, studying the supplier networks and things, which requires not much resources, but many impactful publications in A-star journals and Sci Index journals could be possible. So that's from that perspective, I would like to throw some light on those aspects. So I think this is the beginning of the era of 3D printing. So the first United States patent. So on 3D printing, even though it referred many other patent documents, here you can see that it itself has referred many different documents. So we had the first United States patent coming on 3D printing, which is called apparatus for production of three-dimensional objects by stereolithography. This became the first and the foremost production process. I think you can see him, the Charles W. Hull, holding his replica of a 3D printed objects from 3D systems. So stereolithography apparatus is the first one, which actually started the 3D printing. I think it's not too long ago, considering the history of manufacturing. But it's very very recently, just like 4 decades ago. So we wanted to basically see that in that 4 decades, I am fortunate enough to touch the first 3D printer in the year 1999. And also get my first part in 2001. So in fact, it has been almost 23 years or 24 years of my journey with 3D printing, right? So I got awestruck when I could see that, whatever I knew in terms of modeling So I had a little bit of modeling knowledge at the end of my graduation. And then I was able to convert that 3D model into a physical object, which got fascinated me, and my career ended up in 3D printing, right? So I wanted to do it for my entire life. So it was so rich to see that, without any intermediate steps, like no jigs, no pictures, no die. So we were able to just convert a conventional CAD design, a parametric or associative drafted design, and then slice them and then put that into a printer, and the printer gives you an object. So this is becoming, it has excited me. In fact, I also would like to share that I printed a very small replica of mine in the year of 2016 when I went to Korea. There's a public design house where I scanned my high resolution model and I brought the model here. And with a color 3D printer, I had displayed it in my lab. So probably I think many of the people who have visited my lab would see a small replica like this, which I have printed. But today I think there is, a lot of AI programs. It's a trending one. The Gemini model, the nano banana model, which actually creates a perception or illusion of having you as a 3D printed model. In fact, we did it. In fact, 7-8 years ago, I printed my own model. But now it's like, there's a lot of status. You could see that people are using this AI program to generate as if they have done a 3D printing of their own replica, right? So it has become so much simpler for people to, use simple AI algorithms to generate such thing. But doing that is very, very, tedious, because we have to take millions and millions of cloud points and then process them and then do a surface reconstruction, add colors. I used OBJ file, the object file, and a material template library .mtl file. And then I printed in a binder jetting machine, so which was available to me, right? So we had an object hidden machine in our lab. So we printed a colored model of that. And also I printed a high resolution model using a nearby industry called Monotech. So they gave it the printed model for me after, synthesizing and, post-processing it with the resins and stuff like that. So it was really good to showcase, hold something in my hand and show it to the people. So I'm planning to print a larger version of it. So you can see that, such a technology which provides you, more easier way to convert your designs or, your ideas or imagination into something concrete or a part. We call art to part transitions, right? So which was very exciting back then, right? So okay, so first I will talk about, before I build my case for the supply chain, I would like to give you a basic background about, the hardware software aspects of 3D printing, materials, and then the philosophy of manufacturing, and how the market needs have changed, which enabled additive manufacturing to take limelight. And then social demographic changes in many different countries, and geopolitical, and also the culture of DIY, and proliferation of this what we call this tinkering culture or innovation culture, maker spaces, innovation labs. How our country in schools, you might be knowing that we have more than 16,000 schools that has 3D printers now through the ATAL tinkering labs, and through AICTE Idea Labs, the 3D printers have penetrated to every corner of the engineering institutions in India. So we would see that 3D printers are not now anymore, that you have to go to a city to use it. So you can go to a nearby makerspace or a tinkering lab or innovation lab, or a startup, TBI. You get access to these printers, and then they become very cheap, very affordable. So we'll see all those aspects, right? So one by one, and then how it actually helped innovation. So our country has was able to do the POCs much faster because of the 3D printing or additive manufacturing, and are able to then innovate faster, reduce the time for innovation and the product development life cycles. And the startups was able to get access to very cheap, high quality 3D printing because of the innovation hubs. In fact, you must be knowing about Hyderabad in the T-Hub, where there is a lot of companies being incubated. Most of the 3D printing companies gets incubated in T-Hub. They also run a very big prototyping center with access to very cheaper prototyping techniques, so that startups can accelerate their product development by moving their ideas into POCs into MVPs, the viable minimum viable products, and then take the idea to venture capitalists and then get some funding and push the product to market as much faster as possible and gain the first mover advantage. So these are, aspects of 3D printing, how it has changed. So as I said, I'm going to focus on the whole ecosystem change that happened because of 3D printing around various functions within the manufacturing enterprise. So we'll start with the, industrial automation. We see that, increasingly, the manually intensive factories are still there. If you see the poultry industry, if you see the, even in India, like, so leather industries, they are not even in industry 1.0, right? So they are not even industry 1.0 compliant. So industrial automation has paved way for, centralized automation control, right? So unattended operations. For example, there are lights out factories called brilliant factories, where production has become increasingly, completely automated. So going from manual to centralized to completely humanless operation. Now, Industry 5.0, they are trying to bring the human back. So they talk about human centricity, and then, lack of, it's not for the lack of trust in the machines, but they want the humans to be at the center stage. So they are bringing back the human into the loop. So then they call it as Industry 5.0 from the moving from Industry 4.0. That means like they wanted to basically make the factories safer for employees to work with the machines. The machines and can understand. So in fact, we have three research scholars in our group. So we're also working in industrial automation along with my partners from Center for AI and Automation Robotics. They are understanding how humans and machines can collaborate and work together. So the machines, the robots can understand the human emotions and then try to adjust its speed and its notes its situational awareness. So those kinds of things are happening now. So where the factories we learn to work with machines. Now we are teaching machines to learn to work with us. So that's the, kind of next set of human centricity in AI, human centric manufacturing. It's all about, going to lights out and then again lights on, right? So these are things which is happening as of now. So I think I would like to, start with this first mission that, when we started with the manual milling machine, we retrofitted with some CNCs, right? So, and then we have the full-fledged CNCs. This becomes the first programmable automation. From that, a completely automated 3D printing machine, which can unattendedly run for many hours, right? So for example, even days. So we can load a part and then, after 3 days, there is a machine called, Atlas from GE, which can print up to 2 meter by 2 meter, right? So that takes almost, 3-4 days to complete. So you just start the machine and then go. In fact, if I remember correctly, even in the year 2005, when I started my research with the powder bed fusion machine, so I usually start my printing somewhere at 5 p.m. in the night, and then maybe a day after that in the early morning. So after running it for 8 hours in the night, again 24 hours in the next day, and again 8 hours in the day. So around noon, I used to switch off the machine. So even for a 380 mm build volume, right? So, and only I get a SMS sometimes, when there is a power went on or the recoater shifted the part out of the bed and things like that. So there were almost, mobile alert notifications using in the GPRS era, not even 2G era, right? So it's like there has been a very large scale unattended human operation happening at 3D printers. So 3D printers are capable of, completely automated process, because you just load the STL file and then slice them and then create a tool path or path planning, and then, you forget it. So it takes care of all the other aspects, like loading the material movements and then the lowering the platform, controlling the temperature, controlling the purging gas and environments. So it runs unattendedly, right? So there's a little human presence or even no human presence is recorded. So that's the kind of, automation that we have gone into, right? So, and as I said, this is the level of hardware. So hardware has been become very sophisticated with the PLCs and all those stuff, the improvements in hardware, and also software. The capabilities of software also have improved. So if you look at our humble beginnings of the software, so this is the Sketchpad at MIT. So the first thesis which came out of MIT, the Sutherland's thesis, still it is there online if someone wants to check it up. So this is the beginning of the CAD, right? So the computer design and drafting. So it was actually a touchpad where there was a digitizing pen that you can write on a CRT monitor. So then the algorithms came, the mathematical representations came, and then the hardware for creating CAD has become the graphics cards and the computing power, and they have enormously improved from microcomputers to things like that. So you see that the CAD software market at somewhere around it has moved from 1990s was its peak in the parametric modeling when PTC introduced the PTC introduced the CAD, and then we have many different engines have been developed, the mathematical representations, and also different kinds of CAD have existed. And they have been able to basically see that you can see that SketchUp is developed by Google right now, owned by Trimble, used by many people, and then you have lots of interesting tools for medical CADs. There are more than 50 different types of CADs for jewelry, for medicine, for food, for concrete printing. So 3D printing is not just for making metallic objects. So you need different CAD systems for different purposes. So for example, Rhinoceros, we have a license of Rhinoceros. We use a plugin called Grasshopper. So wherein you can use computational design techniques, where you can actually modify a small amount of parameter, and then that could largely influence the design, right? So we use it for jewelry design, and we also use Rhinoceros for lattice structures. There's a plugin in Rhinoceros called intra lattice, which can be used to basically produce very intricate lattice structures. And then you also have reverse engineering softwares like GeoMagick, right? So you have so all this, these are brand names. I'm not necessarily promoting any of this software, but I'm just trying to give you an overall open source. Like for example, Libre is like open source CAD, so which people can adopt it. And India wants to basically, localize CAD by using LibreCAD. So there's you must be knowing about IIT Bombay, the FOSI, which is typically talking about the tutorials and things like that. They want to. There's a big open source movement which is now spearheaded by IIT Bombay to basically develop indigenous CAD systems and things like that. So just to cut down the reliance, so due to geopolitical reasons. And this is the 3D printing CAD market. If you see the CAD systems that are used, like Rhinoceros, as I said, for jewelry designs, for lattice structures, for apparel design, textile design, and things like that. So, and also nerves. Now it's based on non-uniform rational B-spline modeling. So, and hyperganic for very interesting shapes, hyper shapes. And then the one that actually taken the market by storm is the implicit modeling tool called N-topology. So, which is actually you can produce field-driven and functional-driven design in no time, right? So it also offers an exciting modeling technique. And then Gen 3D and Desktop Metal went bankrupt now. So, but they have their CAD systems available. So I think many companies are becoming, going into bankrupt as of now because of their misplaced priorities or over promises, right? So that they have done. And Altair and Hexagon and Siemens, and they are all CAD systems. They have a very interesting lineup of additive manufacturing capabilities, not just for preparation of the job and things like that, but also for automatic support structure generation, analyzing distortion, simulating even microstructure. In fact, ANSYS can simulate microstructures and then simulate the entire production process, and then also use methods like inherent strain methods to understand the process defects before it happens like that. And Blender is open source CAD. I think you all must be knowing about it. There are many such CAD systems. Metal is a Belgium-based company which has been bundled. The first software when we bought the first 3D printer in 2003, we got Materialized version 3 bundled with the machine. So it has got excellent capabilities that time. In fact, you might be knowing Professor Karnagaran, who just gave a talk just before it. He had a module for LOM, so which was there part of the Materialized. In fact, when the open source revolution started, when Professor Adrian Bayer started the RepRap project, in fact, I wrote the first slicing codes for it. So in fact, my code is still there. You can see in the list of credits, you would see my name there. Only one person from India who has contributed to the open source project, which made the Creality and other printers to proliferate, right? So the RepRap is the first open source printer. The moment when the FDM patent expired and Stratasys patent expired, so the open source project started, and then that was the defining moment for the 3D printing, because that only made 3D printing more democratic. So we have the Bamboo Labs now, Creality and Enders and all those printers, Maker bots, all those things now, Ultimaker, everything came out of that project. So if you see all the boards, motherboards and slicing algorithm still bears the name of the RepRap project. So the Darwin project, the first one, which I am part of. So I think I am very happy to see that we have been contributing immensely to the CAD, slicing and process planning for 3D printing over last 2 decades, right? So there is a fundamental difference, the way in which we have actually moved from conventional CAD to the new design, right? So if you see, this is the original 2-dimensional models that we used with the CSG representations and boundary representations, right? So we moved from there to generative designs, right? So where you can use generative design algorithms, right? So generative AI uses lots of AI methods and machine learning algorithms, like for example, CGAN. Generative adversarial networks, where you allow two neural networks to fight, to find whether a particular image is a fake or not. So that was the defining moment. That paper got 40,000 citations immediately. So it came out of the idea came out of the professor's party, right? So, and then the CGAN algorithm became very, very famous because it allowed discriminator and a generator to basically see the generator generates an image and the discriminator discriminates it whether it's a true or a false. So you are able to learn very quickly about images. So the same algorithm being used now to design, to generate shapes. So with little bit of variations, you can generate thousands of variations of the same design. And in fact, if you so we recently had a publication where we wanted to develop a decision support system to understand the granular differences between these designs that are generated by generative design. So we built another AI system to find out the best AI outcomes. So AI give thousands of designs, right? So like, for example, you have a chat GPT, you ask a poem, you can ask 1,000 times, it will generate 1,000 poems, but you will get, difficult to know which poem you want, right? So then we developed another AI system to find out the poem that really you like in a literal sense, right? So in the 3D printing, we did that. So if you have, let's say, for example, 2,000 different models with minute variations generated through topology optimization and generative design. So our algorithms can, use, structural similarity analysis, another AI technique or ML technique, to basically screen through these parts and then understand the minute differences and rank them based on cost complexity and incremental variations, right? So those kinds of things we are doing in our lab. So I'm happy to share those things with the recent publication that we had around that. So this is a generative design. So you can see that this is instead of feature-based model. So we had a feature-based. Feature means like one feature at a time, like loft, right? So surface revolution, protrusion, right? So blend and those things, right? So we are going into scripting. That is the one that I talked about, the Grasshopper plugin, and visual scripting, like using visual clues to script algorithms, right? So and then gestures, AR, VR, right? So we are now using in our lab we have a AR VR system which had. With, like, for example, the one that we use is HTC-Vive. With the HTC-Vive, you can actually create a very complex 3-dimensional models by using a simple Google G code. So Google code is a open source algorithm that allows you to create complex 3-dimensional models by just sculpting in air with the Vive, right? So these are things which are happening. So and we are now moving into more semantical and structural approach where we define the function first. We have been working at form follows the function mostly, right? So we will give a conceptual designer, we will give you a form, and then we see that whether that form works for our function by doing a CAE and all those stuff. That's what we have been always doing. We do this, the step like concept design, and then we come to the embodiment design. Now we follow the principle called function follows the form, right? It is typically like you give all the requirements to the computer, to the AI algorithm. Like, for example, I say this is the material representation. Currently, I have this is the positive geometry. This is my negative geometry. I need to fill in the spaces. So the algorithm takes care of the generation optimization of a shape based on that you can generate or optimize the shape based on the given load. And then you can do a FEA or validation. So that means you initially define your form. It actually gives a very bionic or naturally inspired and even smart materials, right? So and 4D printing and structures where it could be even shape shifting or based on some external what you call stimulus, either temperature, force, pressure, right? So viscosity and things like that. So you can see that. So you can create such a very complex 3-dimensional shapes, right? So that means we are moving into an era where the 3D models starting from the the sketchpad, the original system to a very advanced level of CAD modeling. So this is some examples of a field-driven design. I talked about this is the one example from the end topology where you can see that you can create very complex shapes, right? So with just a few clicks, right? So and then define parametrically varying. So you give the pressure distribution of a bicycle seat, it will be able to then distribute the load and remove the material in region where you don't need. So it looks so new, right? So it looks like an artistic piece than a bicycle seat, right? So you can see that such a level of examples are there. Or you can also look at here. This is the example of heat exchanger or a conformal cooling, or maybe you would have seen the Raptor engines from where design becomes so simple, but the geometry become extremely complex because they removed all the straight pipes. They would have lots of pipes around, and then these are because you cannot drill holes, complex shaped holes inside to allow the regenerative cooling for the fuel to pass through, right? So, but now you have only a simple structure. And then inside all the complex cooling channels run. So the design has become from complex to simple, but the geometry has become from simple to so complex, right? So you can see that these kinds of variations are possible. And also you can use varieties of structures like lattice structures. You would see here, for example, a lattice structure which could be created. It could be a stud-based lattice or a sub-based lattice. So you have varieties of lattices. You can play with their size. You can play with their distribution. You can play with their arrangements. You can play with the what you call the strut size and strut diameter, and then get structural based lattices. Right. So you can also use AI driven. This is the one example from Autodesk where you can see that you define the problem and then you define the negative and positive regions. So you see these are the regions where you don't want material to put, where there's going to be fasteners, and other regions you define as a positive geometry for the algorithm to basically generate an optimized structure. So the AI generates thousands of alternatives, right? So by solving, what is known as a minimization of the compliance problem. So you are trying to minimize the compliance. Compliance is the one by stiffness. So you are trying to basically maximize the stiffness by minimizing the compliance, right? So that way you are able to solve it. So you have solid isotropic material penalization. You have BISO method, which is evolutionary structural optimization methods. You have bidirectional evolution, structural optimization. So many different algorithms. They are, iteratively and recursively used in an AI algorithm to basically reach a very complex solution and iterate the solution over certain design variants, design fields, right? So you can see such a very complex shapes or bionic shapes are possible using 3D printing. And as such, you will see this is the conventional, production method where you get, you transfer the requirements in a virtual 3D space and define physical location. So all constraints will come in, right? So parallelity constraint, perpendicularity constraint, and then location constraints, and then positioning constraints. You add all those constraints in the parametric three-dimensional model, and then you use either feature-based model or a scripted model, and then you create associative sketch from it. So you have a parametric associative feature-based model, and then you get a 3D model. Then you go for a boundary or volume representation. The boundary representation is typically a BREP model. A volume representation is a CSG model. And then you can create wraps and envelopes, shrink fits for 3D printing. For example, 3D printing cannot print a very large ship. Like, for example, we had done projects with a lot of UAE-based customers where there are oil rigs. They want to 3D print entire oil rigs or architectural models, right? So they would have, very small features and very large features. It is very difficult to basically print them. So because when you print, you will many places you will go, the wall thicknesses can be much smaller. So it is very difficult to print them, right? So then we need to go through a lot of wrap and envelope surfaces. You envelop everything in a watertight model, remove those features which are unachievable, and then you create a very complex three-dimensional model, convert them into simple printable models. So those things you can do it here, and then also you can simulate and then take it for a CAD/CAM to manufacture it, right? So, but here now it is very different. Now instead of going at that level, you can see that they are first of all in the conventional parametric design. This is what is happening. It's in the new design, the topology optimization and Rhino grasshopper design and computational design, AI-based generative design. You can see what they do is they just simulate the rough sensitivities of the design space. Like, for example, fluid transfer or system boundaries. They have multi-physics problems. In topology optimization, many people think it's only for structural problem. Not really. So you can solve a topology optimization problem for a heat transfer problem, or for let's say you can for a flow problem, or sometimes topology optimization with cost constraints. In fact, one of my research students, Dr. Elvis, who recently graduated, did a cost constraint topology optimization. In fact, we added cost as a constraint inside that. So we also had flame retardation function. Sometimes we did have electronic 3D printing where we added another constraint for electromagnetic constraint. So it's like it's possible that you can do multi-physics. So all those interactions and functions independently you can model, and then you can get a 3D sensitivity map in the design space, right? And then highlight the zones of conflict. That is where we define the positive, negative, go, no go zones for the algorithm to put material in. So strictly, there are some zones where it is going to interact with the other part. There are mating surfaces. It's a no-go zone. We define as a negative geometry, or where the geometry should not be put. And other places we define as a positive geometry, where those things will be printed. So then you get a rough zones of conflict. Then you get a rough 3D model. It is visually scripted and is mostly generated. So you normally use implicit modeling here. So we are not using parametric design, parametric modeling, but here we use implicit modeling. Implicit modeling is much easier to play with generative AI algorithms. So that's the reason why Entopology and Autodesk Fusion 360, the generative design model, they all use implicit modeling phenomena, but they do a bidirectional conversion within the engine. So you always get, for example, you can always, once you do the model, because most of your CAM packages accepts boundary representation, B-reps, and so either based on a solid modeling schemes, right? So conventional solid modeling. So you can generate the model, but then convert into a STL file, convert into boundary representation, and convert into volume representation, and then you can wrap an envelope and then simulate CAE, and then go for the design release, right? So you can see that the revolutionary design or the new design process, is typically based on that. So as I said, haptic interfaces. This is the first 3D printer I think many people would have touched their hands on. This is the $80 pen. It's like less than 7,000, 8,000. It's called a doodle pen, where you can actually, kind of a very complex 3D shapes by using a pen. So it's a 3D printer, but it's not held in a CNC structure, right? So very similarly, you can see that the modeling method and the manufacturing method are becoming more or less similar, right? So it is not anymore like 3-dimensional. So for example, if you want to sculpt a 3D model, you can see in a AR/VR digital space, you are sculpting it. At the same time, you can see also you can do the sculpting. So the way you are sculpting, the artist can create a 3D model and then convert that into a STL file and put it into a 3D printer, the way you are actually doing in a doodle pen. So that means we are becoming more easier to basically manage the way that we create the 3D models, right? So conventionally, there will be a flat screen, and then you have a user interface and set of buttons, and then you try to basically click on each button to create definitions of individual geometries, like using a 3-point to create a circle, or a center and a radius to create a circle. But right now you can see that you can do a sculpting by just haptic interfaces, or AR/VR haptic interfaces. So these are some. There is also feedback mechanisms and then sculpting mechanisms, which can allow you to basically add constraints and then also smooth the shapes, right? So all those features are currently available. So this is we talked about hardware and software, the progress, right? So I'll then talk about a little bit about materials, and I'll talk about manufacturing philosophy, and then come back to material, right? So this is more important from the viewpoint of understanding our supply chain repercussions, right? So in fact, in 2016, I had an opportunity to go to Ford. We have a Ford Global Technology Business Center at Chennai. So I was invited for a lecture there. So I went to the Ford engineers. I told them, you are part of the second industrial revolution, right? So, and now in the fourth industrial revolution, how Ford is contributing, right? So Ford has become synonymous with the second industrial revolution or mass production, because this is the Model T car, which was largely 3D printed, right? So then the Ford engineers bought 3 multi-jet fusion here in Chennai offices, and then they started printing at least few parts for the fixtures in the factory and all. But they are the slow adapters to the 3D printing, because they still work with legacy manufacturing process, right? So, but they are very slow to adopt 3D printing. But after many iterations, they were able to then get some good set of parts in the conventional manufacturing lines to use as a jig, use as a fixture, and use as a locating devices, right? So they're still using 3D printing. They have 7 3D printers in the Chennai campus, which are sent to factories in in Gujarat, and also in Maharashtra, right? So now, if you see, for example, so if you see, for example, they had a factory in Chennai, but they closed it down. But they still have some contract manufacturing going on for their tier 1, tier 2 suppliers, where they still support some of these activities. Okay. So this is the scenario of mass production. If you see, mass production where there was we got the concept of transfer lines, right? So I showed you the origins of the 3D printing process from stereolithography, origins of the SCAD from the Sketchpad from MIT. I'm just talking about the manufacturing philosophy origins, right? So I'm discussing about the origins here, and there was a division of labor, and there was a skilled and unskilled labor. Parts were interchangeable, right? So mass production gave us, more labor-intensive manufacturing, and also it has become standard parts have become the norm because we are. I think you must have read about the novel. Yuval Noah Harari's book, right? So the Homo sapiens, in which he mentions the humans started to collaborate in large scale across the world during the World War, right? So that is the time when the humans started collaborating. Now I think during COVID we started collaborating for vaccine development and all those things, right? So but that is the time when humans first started collaborating in a large scale, right? So so everyone was actively involved in the act of war. So during the War I and War II, the World War I and II, right? So that is the time they had the need. Let's say I make a nut in America and then I bring a plane into France, then I need to have a bolt to change that, right? So you can just buy the parts from across the continents and then they are able to be interchangeable. So the military standards came and then the standards, the design of those standard one-off design parts came. And now we are moving away from that, mass production or standardized parts. So we are looking at more hyper customized parts, right? So that is the norm, right? So I think I told about the generative design example. Imagine that, we all came through our school education, right? So imagine going to a first standard class or a second standard class, a language class, typically English, right? So there will be a book and there is a poem, right? So today it's no more done. I had an opportunity to visit a school and they generate a poem through ChatGPT for individual people to memorize. It's like, everybody is memorizing their own poem that they have generated, not written by some, eminent, poet, right? So that means like they are able to customize at the classroom, like 30 poems for 30 students, that they could actually study the poems. And each of them could, identify what they want in the poem. Somebody want a melancholy, so it will be more melancholy. Somebody want, more sacrifice and something like that they can have. Somebody want a nature. So according to their interest, they could do it. So that means the standardized textbooks are now moving to customizable textbooks, right? So similarly, the standardized parts are moving towards customizable parts. So the mass customization is the term that has been in use for last 20 years, like 2000 from 2020. Now the word is hyper customization. They want to basically move from mass production to mass customization to hyper customization, which means like I am customizing the individual product for everybody based on their need, because 3D printing offers that variety. Mass production cannot offer that variety. So let me see why. So the mechanization and everything was there, right? So the reason why, so we started from the product variety, large variety from 1850, and then the manual mass production, it starts to begin when the variance, product volume per variant actually went very high. Here the cross production, you can see that for one, the variant of each product for each product is much higher. That means it's like cross production. And this is the epitome of mass production, the Beetle car, which has the highest number of mass produced car. From there to mass customization around 1980s to 2020, right? So like almost 40 years. And around 2000, then it becomes the globalization, regionalization, and that is where, then the renaissance, the manufacturing renaissance, so-called renaissance, started to take shape. So now the nature of the product is we want to basically move manufacturing into a more decentralized, distributed, personalized production of complex manufactured objects. So that's the theme as we look at it from the industry 4.2 or 5.0. So the mass manufacturing talks about having very high volume, right? So mass customization talks about having very high variety. Mass complexity talks about having very high complexity, right? So, and if you get all the three in a manufacturing process, then you get a complete manufacturing freedom. So that is what I think people think additive manufacturing is a solution for this eighth one, which is typically the complete manufacturing freedom. Because some process gives you variety, but they don't give volume. But some product gives volume, but they don't give variety. And some product can give volume and variety, but they don't give complexity, right? So high complexity. So the only one process that can handle all the three to some extent is typically additive manufacturing. But in the volume, still it has to do a lot of work, because still the conventional production methods are very good, in terms of the scope, economics of scope and economics of scale works very well for volume there. But the economics of scope works really well for, the the additive manufacturing, especially when we talk about mass customized and mass produced manufacturing, right? So I think I want to give you, because we are talking about supply chain and the overall system, it is very important to talk about all the four M's, right? So in manufacturing, we talked about materials, man, machine, and then money, right? So first we'll talk about the man now. So that's the labor, right? So I think Industry 4.0 came out of Germany because they had a very aging population. If you look at the demographics, of different continents here. So if you see 1950s, right? So if you look at the Europe had 21.7% of the world's population. Right, around 2015, you could see that dwindled to 10%. So around 2050, it can go up to 7.3 and only up to 5.8%. So the problem that they face is the availability of the labor. So that's why they want to basically go for a lights out factory. So Industry 4.0 is a document given by Angela Merkel of Germany, right? So it is spelled differently. It's called INDUSTRIE, right? So it's spelled in German. So this document came in 2010. It talked about increased automation in their manufacturing plants. So they termed it as fourth industrial revolution because they have a shortage of labor in that country. But look at the African countries. They are going to basically gain a large amount of population around 2000. Even Asia's share of population is going to decline. So we are also not in the critical threshold of that number. They say that that we are also facing population crisis, like, so we are not able to we are becoming more dependent on easy lives, not the right life, right? So because of that, we are getting our population can get very low. Even though we are number one now, very soon we may see the decline, and Africa will be you can see that they will take up 39.1. So you know that China was the manufacturing capital of the world because their labor was cheap around 80s. So they had a huge number of young people available, and they went on to the one-child policy, and now they are also suffering because of it. So there are not enough labor available in those countries. So the production is now being moved from China to other places because now they have gone to a phase where they are moving from low value, high labor intensive manufacturing to high value, high knowledge kind of manufacturing, right? So they are into electric cars, autonomous robots, right? So all those aspects which are not recording with, they require nimble, very high skilled, knowledge intensive laborers than low skilled workers. That's why countries like Vietnam, Bangladesh, India, they offer a better option for manufacturing companies to get cheaper labors, right? So that's the reason that we will be doing that low intensive, knowledge intensive until we move up in the value chain, right? So then we'll be able to then also become knowledge intensive. Then the entire production can shift to Africa, where they have a very cheap labor available and their population is much higher. So around 2010, you would see Africa being the manufacturing capital of the world. So most of the factories will be shifted there. So this is the kind of one thing that we need to really take notice. So Europe doesn't want to basically lose its manufacturing knowledge, especially Germans and French and then UK. But they also don't want to basically kind of depend on the cheap labor, but they also don't want to lose the edge in manufacturing. So that's the reason why they are trying to basically eliminate the human labor, because their average age of population is much higher. It's not younger people anymore. They are all aged people. So because of that, they are trying to basically take that. But India is trying to capitalize on that, developing automation solutions and then setting up factories there, fully automated lights out factories in Japan. So the Japan case is also same, because they also have aging population. The average age of them is much higher, even though they don't have a very active labor force available there because of the aging population. So everybody is suffering from this population crisis, right? So that's the reason. So you can see the very similarly where the 3D printing is right now having very high growth rates, right? So if you see all the Asian continent, where you can see the 3D printing is growing in large. So that is the direct correlation of the population, right? So if you see that, the regional growth rates for 3D printing market for the last 5 years, right? So from 29 to 2024. So if you see Europeans and other places, the growth is not that high, but if you see the Asian markets, they are actually going into 3D printing and things. That means this is the most happening place as of now, right? So because a lot of manufacturing is being currently shifted to Asia, most of the manufacturing is in Asia right now, in Vietnam, in Bangladesh, and in India, in other places, right? So that's the reason why 3D printers are becoming more popular in India, but they have also have 3D printers, but the market penetration is much higher. And slowly it will shift from here to Africa. So over time, it takes time for them to become, the labor force available, the more skilled labor force available for manufacturing. So this is one slide that you must have seen many times in many presentations. So we are looking at the fourth and fifth industrial revolution. We are moving from mass production to industry 4.2, and additive manufacturing or 3D printing has been identified as a key enabling technology for the fourth industrial revolution. Now, primarily for two reasons. First one is geopolitical, right? So you would see that America is like the manufacturers huge amounts of defense equipments, right? So they want to reshore manufacturing because there is you already know there is a lot of tariff war going on, and then China becoming more dominant in defense and other places, so they are trying to flex their muscles. So the geopolitical reasons America wants to reshore most of the manufacturing. That's why there are programs like Make in America. When I was in US, I was working in NIST, one of the US government organization. It's under US Department of Commerce, right? So it's a very influential organization. The NIST only did the WTC investigation. So NIST is earlier known as National Bureau of Standards. So I was a guest researcher there for 3 years. I get to know how that is the time when all the national manufacturing innovation institutes are established. Right now there are 26 institutes that they have established, which are modeled after the Fraunhofer institutes, right? So the one is called initially it was called NAMI. I think it's called National Additive Manufacturing Innovation Institute. Now it is now called Make in America, or Make in that institute is called Make in America, that entirely focuses on developing additive manufacturing capabilities for America. So in fact, there's a push from the government. So you would see that the Ohio region is the very active region for 3D printing, where GE and all other companies, they have investing huge amount in. GE has its own business called GE Additive. They themselves manufacture. They use. They actually acquired the Morris Tech, which is the #1 service bureau in US that time for defense supplies and things like that. So they are able to kind of bring that manufacturing back. So India is also doing that. For example, in our road, the road that our institute is situated, which is in Chennai, we have a startup company called Agnikul Cosmos. They are also incubated by IIT Madras, but they have a factory here. So they make the entire 3D printed engine. So you see the engine that you see here, the same engine is being also 3D printed in Chennai, very close to my campus. There is a IIT Madras campus in our road. It's called Tayur campus. It's called Discovery Campus, IIT Madras Discovery Campus. There are many startup companies. One of the startup companies called Agnikul, and they make 3D printed engines. So with a large 1 meter by 1 meter machine that they have, they are able to 3D print a complete engine. So they are able to develop that engine for low payloads for launching satellites, right? So this is the space rocket. So you can see that Elon Musk uses his rockets. So there is a company called Relativity Space, and there are many 3D printing companies which provide parts for Tesla and also for SpaceX to basically do 3D printing for automotive and aerospace applications. So, and also GE and GE Aerospace for aero engine components. They have actually, you must have heard in so many other talks about how GE has certified many AM components to use in LEAP engines and the fuel nozzles and other things. So those are poster boys of success for 3D printing, right? So if you look at the geopolitical, right, so Europe actually has so many different programs. So when we started the Make in India program, similarly, if you see UK has high value manufacturing catapult programs, Innovate UK, and then Belgium has made different programs. France has so many different programs, Plan Industries de France, Transition Numeric Q, and Industry to the Future. And Portugal has Produtec. And then Spain has Industry Connected or Industry 4.0. Italy has called IoT and Industry 4.0 or Fabrica Intelligenti. So in Europe, they call, typically China, they don't call Industry 4.0, they call it as intelligent manufacturing. US also doesn't call Industry 4.0, they call smart manufacturing. Because I was there when they wanted to coin an alternate term for Germany, but they wanted to take on Germany. So they coined the term called smart manufacturing that essentially translates the same essence as Industry 4.0. And then you see Germany has Industry 4.0, Platform Industry 4.0, and Slovakia and Czech and Austria, all countries have their own program. So there are a lot of government push to bring 3D printing into mainstream. That's the reason you will see 3D printing is becoming extremely popular in many countries, and many institutes and universities, they started their own research group. So if you look at most of the metallurgical departments, materials department, civil engineering department, food science department, biomedical department, mechanical engineering department, ocean science department, you can spot 5 or 6 researchers in additive manufacturing. So because you can use the same additive manufacturing or 3D printing process to print food, print organs, print homes, right? So print chocolates, you can print meat, you can print pharmaceutical items like tablets, you can print metallic and polymer and ceramic and metalloids, right? So you can print so many things, right? So that's why the many departments started their own research in additive manufacturing, catering to the needs, and then it has become interdisciplinary, especially algorithm part, CAD development for protein patterning and things like that for organ printing has been there. So lots of new ideas are flourishing. It's one of the most progressive technology as of now in terms of funding. So if you look at the recent AMT funding, even with our internal DST funding, you will see additive manufacturing has very high focus there, right? So this is like, becoming the next progressive technology in mechanical engineering, at least for some time, just because of the government push, geopolitical reason, material development, labor shortage, right? So many factors are there. So looking at the Indian manufacturing, right? So I've been reusing these slides for many times, right? So our Indian manufacturing is not, some manufacturing is not even industry 1.0, and some of them are very advanced. Like for example, this GE plant in Chakan, which is a brilliant factory. You will see only a few humans here, but most of them are automated. So these are like semi-automated factories, like the BMW assembly factory in Chennai, which is very close to our place. So we visit there, they bring the knockdown units and then they assemble it here. So you can see Sachin, the role model, the brand ambassador who is assembling, the engine for a BMW. And this is another engine assembly plant for in Chennai, Ford one. That right now they don't have, but so you can see that tier 1 manufacturing in Ambattur near Chennai. So it's like a full-fledged manufacturing for automotive tier 1, tier 2 components. This is in Pune, and then there are factories everywhere. Like there's a very large automotive cluster in a place where we have, and we also have textiles and other mills and other things are there. But if you see the leather industries here, so like they are still in the not even in the 1.2, right? So that means they are not even mechanized. So they are not using any personal protective equipments. They are not using any safety equipments. They work with very carcinogenic materials like arsenic and mercury, and they process leather manually, right? So it seems like our manufacturing industry is too diverse. So that's when we developed a capability maturity model to understand whether they are ready to implement industry 1.0, 2.0, 3.0, 4.0, 5.0, and so on. Like, so what stage they are in. So that is a very important task for Indian manufacturing industry to understand and thrive, right? So with that said, why 3D printing is gaining a lot of importance in India is primarily for 3 reasons. One is because we want to always leapfrog, right? So we don't want to go through 1, right? So then 2, then 3. So we want to basically, like for example, digital payments, we didn't had, so our ATM, for example, 1960s US, the ATMs were used. We got it only around 1990s, right? So in the close to millennia. But we have got QR payments so quickly, right? So that means like we want to leapfrog to industry 5.0 directly from without passing on stages, right? So that means like India wants to be also taking a small pie in 3D printing market or additive manufacturing market. So that's the reason that India also pushes a lot of additive manufacturing. MeitY has spent a lot of money on additive manufacturing programs and schemes through NEELIT and other agencies, and then they are also funding a lot of projects in additive manufacturing, right? So they have their own government push through many ministries. So this is like, we talked about manufacturing philosophy, hardware and software. So materials point of view, we also got a lot of new materials. For example, we have been using metals, composites and polymers, right? So we have quite long time, right? So in fact, we have gone from Stone Age to Bronze Age to Iron Age to steel to polymers to silicon. Now we are in the plastics age, right? So polymer age, we have moved to now what is known as high entropy alloys, right? So we are talking about alloys which could be alloyed during the processing, right? So we call functionally gradient structures, smart structures, oxidic materials, right? 4D printing structures, smart materials, right? So we have so many different class of new materials, including biomaterials and very high capable, biopolymers and also polymer-based composites, both thermoplastic and thermoset composites, right? So now we are looking at, material inventions are, a large amount of invention is happening. So the manufacturing process also need to, be able to process these materials, right? So for example, a functionally graded material is very much possible in a hybrid additive manufacturing, where it involves direct energy deposition with multiple wire feeders you can deposit, right? So the material is also pushing, and also we have this different materials and capabilities of different manufacturing process. You can see that. So thermoplastics, photopolymers, metals, ceramics, composites, biomaterials, multi-materials. So we have so many different kinds of materials and so many different kinds of process. So we see that the 3D printing industry is also pushed to innovate based on the new materials that are also available, right? So that gives a very interesting perspectives about how we can make 3D printing process with very high mechanical properties, good surface properties, and reduced cost. We are able to then use many different types of materials. So polymers, metals are the defining moment in 3D printing, but also now we are now moving to electronics 3D printing, food 3D printing, concrete 3D printing, tissue-based 3D printing, protein printing, and all those aspects, right? So that is becoming. And next important driver, right? So if you look at it's DIY, right? So many people want to do tinkering. They want to basically, do a lot of the schools have started this program, colleges have started this program. So 3D printing has become ubiquitous now because of every school is adopting a strategy to provide a space. For example, we have 3 government schools nearby. We support using an NGO called Capgemini. There's SRF Foundation. So through SRF Foundation, we have set up STEAM labs like 3D printers, CNC machines. We make those 3D printers in our home. So we had a 20,000 square feet mother maker space, which is basically which makes 3D printers for other maker spaces, right? So then students come here and then they fabricate the machine. So this is one CNC milling machine and 3D printers. They machine the components. They buy the commercial off-the-shelf controllers, PC controllers. They make their own 3D printers. So we use DIY philosophy to proliferate 3D printers. In fact, that place is the most visited place. So far, 55,000 students have come to just have a orientation, which is called the makerspace orientation, to visit the 20,000 square feet lab. So it's a 6-floor lab, so that we have established during the pandemic. And before that, it was in a small space of 5,000 square feet. So the last 5 years, it is functioning at 5 different floors. So we had so many different manufacturing methods for students to realize to make a makerspace on their own, so they can come here, make machines, and take it with them. So that's the kind of DIY culture has increased the adoption of 3D printers, and then also made possible that the people can make certain stuff, right? So we know that DIY culture is good because that is what the open source proliferation objects, open source hardware directly came from 3D printing innovations, right? So that's the idea. So maker spaces gets a lot of push for 3D printing. So this is the maker culture. You can see that students come with this is a faculty from Coimbatore. So there's an institute called Ishwar Engineering College. So it comes with a practically oriented students, right? So and then they make their machines, the basic setup machines. So it's like it has become extremely affordable for them to make their own machines in our facility and then take it with them at the end of the internship period, right? So you can also see a lot of school students come to visit our place. It's like we have been using this DIY culture to promote the adoption of 3D printing in schools. And in fact, many schools we support, they went on to participate in first robotics competition. They won Rising Star Awards and Gold Awards many places. In fact, the students from many other colleges who come and use our facility and 3D printers, they went on to win the global recognition in ROV challenges, solar challenges, Mars rover challenges, and SAE competition. So many competitions they are able to win, and also competitions conducted by the Smart India Hackathon, Smart India Hackathons, Flipkart Challenge, and so many different companies. So students are able to then participate because they come to the lab after the class, the practice class in the evening at 5, and they spend up to 12 in the night to just realize some ideas, make the prototype, and then they're able to then use that facility, right? So this is the kind of thing that are happening. So also the that the prototyping was 3D printed prototypes is in use for quite a long time, but it's also another push. So the people in the product development wanted to have 3D printers. So the one place that you will see 3D printers from the beginning of the time to today is where the product development space is. So where they want to use it for prototyping purposes, right? So I would like to show you 2-3 hype curves in 3D printing before I go into the supply chain part. If you see here that 3D printing hype curves, I have been following the hype curve from 2012. Every year when the Gartner document gets released, I will look for the page where there is a 3D printing hype curve, and then I just record it over time. for people to basically use it. So this is around 2012. So you would see that 3D printing is at the peak of the expectation. So that is the time they thought 3D printing is going to change the entire world. So you can print an entire study virus, you can print your entire home. So it was at the peak of inflated expectations, right? So, and then it has reached a trough of fulfillment in 2016. By 2020, only few applications survived, and many technologies, over time has been survived, but 3D printing is going through a churn right now, right? So this is around 2014. You could see that many different technologies like 3D scanners, 3D printer for prototyping and all there. But personal and consumer 3D printing is still at the peak of the inflated expectation. But the innovation trigger is happened for macro 3D printing, bioprinting and stuff like that. And then if you look at 2018, that is 6 years after, you would see that many technologies have matured, like printed electronics. There are few companies like Nano Dimension, others. They were able to get surgical anatomical models. There's a medical college nearby, which is called Savita Medical College here in Chennai. So they have a digital anatomy model printer, so which is a very expensive printer, which prints a complete digital anatomy model, a transparent model for it. So you have a complete suite of production methods to get a digital anatomy model like that. So we have lots of this been commercialized now, which was there in this thing. Now, if you see around that time, it is blockchain and 3D printing for security, bioprinter, oil and gas, right? So IP protection, they are a part of the innovation triggers that time. But I would like to tell you, right? So there are a lot of enablers for 3D printing, especially from the industry 4.0 perspective. To summarize it, so we moved from IT revolution. From the Indian story, we said right now we want to basically go into the industrial revolution. So we want to basically move to the fully automated, but that doesn't mean that we want to eliminate the humans, but we want to keep the human at the center. But we want to automate the entire production process to move them from a laborious employee to laborious worker to a knowledge-based worker. So it could be more nimble and develop products, and then products and process systems will change. And also the convergence of many different technologies. And then we have sustainable, additive and smart manufacturing as a theme for the next generation of manufacturing, right? So with that said, I would like to take a little bit of time to explain how 3D printing has become an enabler for many industries. Industries wanted to adopt 3D printing, but where did they find the value for 3D printing? That's what I want to spend a little bit of time here. So there are different levels of enabler. One at the product level, which is the first level, and the chain level, which is the second level. And also you have the life cycle level, which is the third level. Okay, so is it audible? Can I get a feedback from someone? And am I audible?
Yes, sir. Yes, sir. Yes, sir.
Yes, sir, you are audible.
Am I in the call? Can someone confirm that I'm audible here? Hello?
Yes, sir, you are audible.
Yes, sir, you are audible.
Just give me 1 second. So I think.
Sir, you are audible.
Is it audible?
Yes, sir.
Okay, thank you. Thank you for the confirmation. I think my speaker got turned off, so it seems like there's a timer there. So hopefully, I think. So
Okay, no.
Okay, it's fine, right? So how much time do I have? So how much time do I have? So is the organizers around here? Okay, so anyway, I think so I'll proceed with them. Still, I didn't get any information from people, so I'll proceed with it. Okay, so I think there was some issue with my speaker. So anyway, I think fine. Okay. So we have enablers and objectives, right? So we have personalization, individualization, and customization as the main first enabler, which talks about moving from one-off design. I explained about how we have moved from mass manufacturing to hyper customization. Second one is digitalization. The entire product chain become digitalized. So we have become from a conventional supply chain to a digital supply chain. And then functionalization, the product become more functionalized, right? So we are able to add more functions into the product by combining many different parts through part consolidation. And then you see that the process chain got simplified, right? So that is simplification. And the manufacturing become more decentralized. That is decentralization. And then it also become more servitized because the Uberization or servitization angle. And many of them get localized, right? So and then it enable a lot of time compression. So these are the major enablers, and for different kinds of objectives. So reducing the lead time, or reducing the product development time, improving the part performance, or improving the image on brand for that product, and then building a very good business case around it, right? So
Yes, sir.
yes,
Sorry to bother, sir. The closing time will be around 6:30, sir. Can you please conclude it around in
6:30.
5 to 10 minutes?
Yeah, thank you. I think this is what I was expecting from the organizers. So thank you very much for reminding me with time. So because it's very important that we finish in time, right? So okay, so this is the one. So if you see that, I talked about the personalization angle where we are moving towards mass customization by having, more number of parts. And then also it is completely digitized. I call this as a 4-step process, like plan, prepare, print, perfect. So entire thing is digital right now, right? So it's like fully digitalized supply chain. And also it is more functionalized, right? So you can add more functional devices like electronics and optimized antennas and stuff. And you can simplify the product by through consolidation, as I said, instead of you can reduce the assembly times and things like that by consolidating using part consolidation. And also your production chains are becoming more distributed and decentralized than a centralized production. And also if you look at the product life cycle, so in the development and prototype, it provides a faster iteration, and distribution and manufacturing, it provides decentralized manufacturing and on-demand printing, right? So it can be servitized, right? So the servitization angle, the decentralization angle, and also time compression angle is there here, right? So these are the things. And also time compression, as I said, it reduces the production time for many production process. And also it increases the level of automation, right? So we are moving from a labor intensive mechanized to, cognitive level of automation. So right now with the digital twin and physically aware AI, so we are moving towards the level 4 automation where we are talking about, so we are talking about orchestrated production or a workflow based production to autonomic productions to cognitive. We are looking at more cognitive production. We are looking at the level 5 of the automation, which is very close to the, the highest level of automation. So that's what we are talking about. So currently, if you see that, so we are looking at self-configuration and self-optimized manufacturing process. So that is the capabilities of additive manufacturing. So this is the factory of the future. We talk about, 2 robots building a bridge, a robotic system autonomously building a very large component, right? You can see that it is building the reinforcements as well as the cements and concretes. So they are able to independently build robots. These are like futuristic vision. Or maybe like, a swarm of robots trying to build a large structure, like, multitudes of swarms. And then we call this as, auto-factoring. So because the word manufacturing, manu means by hand. So we are moving towards drone-based auto-factoring. We call drone auto-factoring. So we have a project called drone auto-factoring. We are looking at swarm of robots to manufacture a very large object, right? So wherein it's very complex dynamic problem to manufacture large. These are becoming the factory of the future. Okay, so now I will try to conclude based on the supply chain. So what are the supply chain implications, right? So because in the supply chain, you would see the traditional supply chain, additive manufacturing supply chain. If you look at the source, plan, source, deliver, we call this model as a score model, right? And if you look at the score model, so if you see it is becoming more centralized planning to the dispersed planning, IP cost has been recouped with the design cost, and direct to consumer distribution without any distributors and retailers, and also one-step production process instead of having multiple steps, and also consumer demands, on-demand manufacturing, because customers can upload the design, download and get the part directly, or they can choose a design which is already available. So IP and design licensing and centralized design is possible, right? So you also, look at the OEMs, conventional supply chain. You have a transport to take it to OEMs and then again transport through shipments to local and then again transport. But in additive manufacturing, you have a local additive manufacturing facility. So through cloud, you have OEM approved parts and standard things. So the end user is that it has become shortened. So it reduces the supply chain risk. For example, you must have heard that, a ship in, one of the, it got a little bit of stuck and then for a month, billions of goods are actually get stranded, right? So natural resources, geopolitical rates, supplier bankruptcy, all long lead times can be shortened with additive manufacturing supply chain, right? So, and it involves huge risks now, as of now, because you see there is an intellectual property theft because you have to, when you do servitization, you have to send your designs across the shore, or sometimes you have to manufacture with the printer. So there will be quality inconsistencies, cyber security. So we have to do the data analysis and then do a risk analysis and assess risk and, possibly understand the supply chain risks there. And also, if you see regulatory and compliance challenges, if you see the additive manufacturing, there is a lot of lag in the standards development. If you see the supply chain impact of high variety, right? So this is the high demand. So you can see the business models of mass customization, manufacturing at the point use, right? So manufacturing closer to the customer or pushing manufacturing close to the customer, reduction in the inventory. These are possibilities of supply chain, right? So the risk mitigation strategies are, having a secure 3D chain. I think a cyber security framework where you can send IPs very confidently and have good certification protocols for minimizing the risks involved in the compliance, and cost of compliance can be also reduced, and have redundancy and backup planning in case of, for example, today, if somebody shuts down the entire supply chain due to geopolitical reasons, so you will have alternate supply chain. So you will reduce the supply chain risk and capability. So we use that, a mathematical formulation called Hershey-Hindal index, right? So which actually reduces the, supply chain risk of key materials and minerals as well as for supply chain routes, right? So we can use all those things to optimize. And if you look at the cost also, in the traditional supply chain, you can see that there's you have supplier, then supplier, manufacturer, and retailer and consumer. Now, if you see that you have a 3D model provider like ShapeAce or something like a GrabCAD or anybody who is providing a design, you just download and print in your backyard, right? So that's becoming more simple. Or you own your printer and print it, or you can go to the nearby shop like a Xerox shop. You go. So instead of ordering some book in Amazon at some time and then waiting for the book to be printed in a centralized location, you go to Xerox shop, you download from Amazon that e file and then print it and then take it immediately, right? So you don't have to wait for it. So these are becoming more like that. So I'm just giving an analogy. So you have reduced setup and tooling cost because of that. Higher material cost has been reduced, and it is becoming lower economics of scale. So sustainability wise, you can see that the entire life cycle becomes, the reuse and everything becomes reduced waste and energy. You can see conventional global production supply chain having raw material to be shipped everywhere, right? So you can see in 3D printing, you have a 3D printing production, either in scenario one, you ship it, or you can have a centralized distribution center, or you can have your own 3D printer. So you can have a 3D printer at the same scenario, like instead of having a distribution center, so you can point of use, it could be very close to point of use, and it could be recycled at the point of use. So that is typically a very important sustainability concern for it, right? So, and skilling the people, right? So there is a lot of skilling that is required. For example, I talked about the Amazon, right? So instead of ordering a file and then order transfer to the warehouse and then product delivery, right? So you can, instead of you eliminate the trucks, right? So you have a truck with a 3D printer, they are roaming here and there. So you order a file in online and then the truck which is nearby to you can 3D print and deliver it. So these are some very interesting, disruptions in the supply chain design and supply chain network which are happening. For example, for critical parts in the battlefield, already we have part ambulances and part doctors. We have lots of 3D printers on wheel. In fact, in American manufacturing industry, they want to basically put 3D printers on wheel so that the inventory earlier, if you talk about the original supply chain, where we talked about Dell and 7-Eleven, where they had the inventory in the trucks mostly, right? So you order then the product, it's a pull method, right? So now we are talking about moving the production or factory on wheel close to them. So the production itself is on the wheel, right? So these are the kind of very disruptive supply chain models which are talking about. So we need to integrate them with digital twins and IoT, right? So we need to have physical shop floor and also a virtual shop floor. You can have shop floor based service systems. So we can control the production. As I said, it is much easier to use data driven manufacturing, digital twin and AI driven, physical driven, all those aspects, right? So you can have supply chain optimization very well done. And also there are a lot of strategic things. So for example, in a conventional traditional manufacturing strategy, the geopolitical risk was there. So the traditional supply chain had, high global flow of goods. Now, if you can localize and decentralize the production in small distributed manufacturing warehouses. So you can see that only centralized manufacturing sites are very small, which manufactures the material supply chain like filaments and other things. So you'll have local manufacturing. So demand of local and customers. So you can see the regional small scale economic cycles can be there. It can improve the employee well-being, and also it can allow the material footprint, carbon footprint can be reduced. So supply chain network redesign can be done. Also, you can make if you want, or you can buy. Those decisions can be taken by the customer, not by the factory. So you're pushing every decision close to the customer. So the key takeaways for today, as suggested, right? So we want to basically talk about how 3D printing has enabled industry 4.0 with the rapid revolution in terms of CAD, software, hardware, and then geopolitical reasons, and then the DIY aspects, and then the material developments, and then the process developments, and also the process chain and our enablers like time compression, decentralization, functionalization, individualization, customization, right? So all those aspects which actually enable 3D printing to be adopted by the industry. But ultimately, we need to look at sustainability, which is the very key. Look at sustainable dimensions like economic dimensions, environmental dimensions, and societal dimensions. We have to carefully study how the life cycle emissions of the 3D printing are there, what to do. So if you know already we have PLA, which is like biocompatible polymer, it's a biopolymer which could be recyclable much easier. So we already have a very good sustainable angle in terms of material, but the consumption of material, wastage in the production process, they are also minimum compared to conventional manufacturing. But you look at all the big picture, the life cycle impact and life cycle cost impact analysis needs to be done. The sustainability impacts of additive manufacturing needs to be well understood, right? So, and we have to also evaluate the opportunities and risks. We have to find a good balance in terms of additive manufacturing can be adapted in supply chain. Reduce the overall supply chain disruptions and risks associated with the disruptions, right? So that said, I think I would like to close my session today. I hope I had given some idea of starting point of research, some very easy research questions that you can ask is like, how do my supply chain changes from distributed manufacturing to personalized manufacturing to decentralized manufacturing to centralized manufacturing. I can study the, different metrics of supply chain like responsiveness, cost, agility, right? So, and resilience with these changing parameters. So you see more, there are a lot of papers that have recently come on additive manufacturing and supply chain in that particular direction. So I think there could be thousands of research questions could be formulated and that could be solved, and imagination is a limitation. So with that said, I may take few questions if organizers allow me to answer it. So thank you very much for your patience listening. That's the end of the session.
Thank you, sir. Dear participant.
Sir, good evening, sir. So myself, Karthik from Rajalakshmi Institute of Technology.
Okay, sir. Thank you. So what's your question?
Actually, you have given that the information regarding that maker space. So I want to utilize that space for as a like an industrial visit to my students. Is it possible to?
So I think
So make the
Rajalakshmi students have come here. Many students have come here. The computer science, mechanical. So most of the students have already come here. I think I am in touch with the automobile department, mechatronics department. So they have already come. So many students.
Maybe you will be speaking about Rajalakshmi Engineering College, sir. Myself, so belongs to Rajalakshmi Institute of Technology. It is another institution.
I'm sorry. I'm sorry. So we call it REC here in Chennai, which is called Rajalakshmi Engineering College. Sorry to.
This is all right. Yeah. Sorry. Do you have any contact details of yourself? Means
so you can write to tlc@iittdm.ac.in. So I'll type it in the chat window. So
okay.
They will be able to respond for any visits for your students or internships or engagements. Right, so.
Yes, sir.
Any other questions? So you can write to this email ID.
Yes, sir. Thank you, sir.
Dear participants, if anyone have any questions, you may ask now.
I know that I went a little faster in the session, so I was understandably that you will be able to follow, right? So hopefully you are able to follow. So if there are any questions, you can answer. You can ask now, but also I already gave my email ID. I'll also type it here. You can write to me if you need more information about any of our research. So or you want to get engaged with collaborative work, or you want to invite me for some other sessions. So I'll be happy to provide my email ID here in the chat box. Sorry, I think there's a small typo here. So Kumaran. Okay, you can write to me in this email ID. So it's called skumaran@iittdm.ac.in. So I'll be happy to support you, right? So thank you very much.
Thank you, sir. I sincerely thank you for taking the time to share your knowledge and expertise with us. Your session was truly insightful and enriching. The practical examples and valuable guidance you provided will surely benefit us in our future learning and professional journey. Thank you, sir.
Thank you.
Hello, sir. Hello. Hello.
I think I got a question here in the chat
Yes,
box.
sir.
So do
Yes, sir.
you want me to address that question?
Yes, sir. That question was, what challenges do you exactly while working on AM?
Okay, so I think I painted a rosy picture of AM, right? So I said AM can do that, but I never said what AM cannot do, right? So I think that's part of, even for another 1 hour lecture, right? So AM cannot do many things, right? So for example, looking at the accuracy, right? So still we have long way to go to get the level of accuracy that the conventional manufacturing process can give. So that's the reason we are trying to hybridize the additive manufacturing with conventional manufacturing. So hybrid additive manufacturing machines are becoming popular. So in one single setup, you can make a AM and then finish those compounds. Support structures are a really pain, right? So if you want to make very precise, high accurate objects through powder bed fusion, cleaning and removing the support structure, you have to build the support structure, right? Design them, build them, and then remove them and finish them. That's a very painstaking process. So that's the biggest challenge. So optimizing support structures or printing without supports is a challenge. And third is directionality in terms of properties, right? So we get 3D printed parts which are typically, very high directional in nature. So you will have properties tested in different directions. They will all be different, in strength in different directions. So and sometimes they are having inherent porosity, so they may have other issues, right? So getting a 3D printed part first right time is still a challenge. So we'll have lots of in situ process measurements, in situ process controls, digital twins, data-driven models, simulations, physics-based simulations, but still it's very difficult to get the first part right. So that's why in India, the Similac, you must have heard Dr. Ram Prabhu, he must have given some session at some point in time. He tells about, there is not even one single part that has been, fine flight worthy in Indian aerospace parts, right? So in US, at least few parts have been, many parts have been certified. So here it is very difficult to certify. So that is one of the biggest challenge. Qualification, certification is a challenge. So where you have to qualify for medical parts and aerospace parts, that's the biggest challenge. So we have very lengthy procedures, and cost of the materials and cost of the machines is still expensive. So it is not very affordable. The metal machines are very expensive. The material is very expensive. So even though democratization has happened through some Chinese cheaper low cost machines, but still they are really expensive because the laser is expensive. The energy, whenever you want to get high intense energy in a very small area, so you need to spend a lot of money. So the lasers are becoming, they are highly energy inefficient. So CO2 lasers are 6%. They have been replaced by fiber lasers now, but still they have 34%. So still now the IPG lasers claims they have developed 67% efficient lasers, but it has been not tested. They are very expensive even to adopt. So right now we are working with 35% wall plug efficiency, which seems like, you have to have spent a lot of energy cost. They are not energy intensive, so they are not really sustainable as of now. So wire arc additive manufacturing and other processes are becoming cheaper alternatives, but they also suffer from warpage, distortions, thermal distortions, and then controlling the porosity, and then homogeneity in the spots, and then all those issues are there. And then metallurgical challenges, right? So in working with multi-materials is a bigger challenge. In terms of polymer, again, we don't have still a commercial durable polymer other than polyamide or ABS, which are really long-term durable parts are very difficult to produce. So ABS parts are really good, but they still carry a lot of pollution and other things. The recyclability of those polymers is still a question. But we can use PLA, but they are not of that really high quality because they are hygroscopic in nature. They absorb moisture and things like that. So polymers, and we have not tasted success with even bioprinting, right? So we have some engineers from Israel have demonstrated, but still there's a long way to go. So concrete printing, again, we are printing homes, but still there is a lot of challenge in terms of getting the structural rigidity and strength and things like that. So we are still demonstrating it. I think if I want to just give a positive note about it, the other speaker, Professor Karnagaran, eminent scientist in India who have been working in this area for a quite long time, like 35 years. He put it nicely or summed up it nicely that it takes time for a technology to mature. So we'll have over time it will mature. It will take time, but these are the challenges, right? So the cost is a challenge. Materials, very limited materials available now, not being, and qualification is a problem. Properties, and then support structures and accuracy issues are still plaguing the AM process. These are the, but we engineers love the challenge, right? So that is where my first PhD is about improving the shrinkage and accuracy of the parts. So we did a lot of very good shrinkage modeling and shrinkage compensation to understand non-uniform shrinkage in nylon 6/6 parts, polyamide 12 based parts in PBF. That's what my first research, my first few publications, which are very impactful, right? So I'm very happy to be in this field, contributing to this, the growth of this process. So generations of engineers will surely make this process as good as the conventional manufacturing process. So at that time, I'll be here or not there, but I'm hoping that these things will happen over time. Thank you.
Thank you very much, sir, for sharing a great information to us.
You can leave.
Can I leave the meeting? Is it okay? Is it done or?
Yes, sir, you may leave. Yes, sir, you may leave now, sir.
Okay, thank you very much. Thank you. I think I would like to thank all the audiences and also thank the organizers for giving me this opportunity. I'll be happy to come back again, maybe in person to visit your college and also speak in person. Thank you very much for the opportunity. Thank you very much for the participants, also for the patience listening and good questions. Thank you. Bye.
Thank you very much, sir.
Thank you, sir. Dappa garu. Bodo shayad